Question 4 is all about a collision between two vehicles traveling along a straight road. Immediately you should start thinking linear momentum. Another part of this question, as you'll see in a moment, is to do with energy because there is some energy lost. So there are a couple of different models that come into this. But the biggest thing you need to access this question is your understanding of linear momentum. Let's continue reading through this question, and I'll highlight a couple of important points before moving on to the actual questions asked. So firstly, you've got car A traveling initially to the east with a velocity of 12.5 meters per second. Car B is initially traveling west, and the initial velocity of car B is one of the unknowns that we'll need to find in this question. The final position of the vehicles is over here. The vehicles started at point X, and it was determined that the distance between the starting point and the final point is 8.4 meters. We know the mass of car B, 3,600 kilograms. We know the mass of car A, 2,400 kilograms. Basically what happened is the collision took place here at point X. So at this point, this is where we are going to make use of momentum, P. The cars then locked together. Cars were locked together. This tells us that we have a completely, perfectly inelastic collision. So that just tells us that kinetic energy is not going to be conserved. But momentum will still be conserved because during the collision, it's an isolated system. What happens between point X and the final resting point is the two-car combination is affected by a frictional force, and it eventually comes to rest. So during this second part of the motion, so we'll label this collision as part 1. Part 2, you've got a loss of energy with friction coming into play. Okay. And this loss of energy we can look at in the context of the work-energy theorem. Let's get on to the actual questions. Question 4.1 guides us in nicely and slowly. It asks you to state the principle of conservation of momentum. Okay. A couple of things that were quite important. You do need to use the word total, you do need to use the word linear, and you do need to talk about an isolated system, and obviously you need to state that momentum is conserved. Without every single one of those points, you can't get full marks. After they've asked you question 1 about stating the principle of conservation of momentum, that does give you a little bit of a clue about what to use later on in the problem. It'll be a problem somehow involving momentum conservation. Let's move on to question 4.2. In question 4.2, we don't use this momentum conservation just yet. We actually need to work backwards. Okay? So what we're going to be doing is we're going to be making use of the definition of work. We're asked to calculate work done. So we're going to make use of the definition of work to calculate work done by friction to bring the interlocked vehicles to rest. Here's the formula we have here. You do need to make use of it straight off the formula sheet, but you can introduce useful subscripts. Here we have subscript F standing for friction, so this term WF is the work done due to friction, and this term capital F subscript F is the frictional force. So work is force times displacement times cos theta. And remember, theta in this formula is the angle between your force and your displacement. Magnitude of the force, we were told, was 7,500 newtons. The total displacement, the cars underwent a displacement of 8.4 meters. That was the distance that they skidded after the collision. And friction and your displacement act in opposite directions, which tells you that theta is 180 degrees, and therefore cos theta will be -1. So overall, when you perform this calculation, you'll find that the work done is -63,000 joules. This negative is important. Work is a scalar, which means it doesn't have a direction. It has a magnitude only. So this negative isn't telling you anything about a direction. So it would be incorrect to say to the right or to the left or to try give a direction. But this negative sign does have meaning. It does have significance. What it tells you is that work done was negative. And if the work done was negative, it means energy was subtracted from the system. The system has lost energy. And this makes sense. Friction has been acting on that system. The system is slowing down due to this frictional force acting, and it is losing kinetic energy. So it is important that you leave the negative sign here, and it's also important that you don't try to interpret that as a direction, because work is scalar. You can, however, interpret it as a loss in energy. And then lastly, there are just a couple of options if you wanted to give your units in kilojoules or possibly in scientific notation. In question 4.3, you're asked to use the work energy theorem to show what the speed of the interlocked vehicles immediately after impact is. And you're asked to show that it is 4.58 meters per second. The work energy theorem, as you're probably used to seeing it, is probably something along the lines of work net, or your net work, is your change in kinetic energy. If you rearrange that more traditional way of writing the work energy theorem, you'll arrive at this particular point. A statement that says your initial kinetic energy plus work that you've done must equal your final kinetic energy. In this particular case, the only force that is doing work on this object is the frictional force, and that's the work that we've just calculated in question 4.2. Substituting values, or rather expanding this formula a bit further, kinetic energy, that's half mv squared, so here's our half. M, this is the mass of the interlocked vehicles, so it needs to be mass of object A plus mass of object B. So that's what you see over here. And v squared is the v squared that we are trying to find to show that it equals 4.58 meters per second. WF, that's still the work due to friction, which we'll substitute in a moment. And then EKF is 0. Okay. We know that it's 0 because that is after they've skidded to a halt and they're at their new location. Substituting values in, the mass of A is 2,400, the mass of B is 3,600, the work due to friction is negative 63,000, and this is important. Performing the calculation, isolating V, you will find that it is 4.58 meters per second. Question 4.4, you are asked to calculate the velocity of vehicle B just before impact. This is the momentum problem that we need to make use of. We have an initial velocity of object A. We have the final velocity of the interlocked vehicles A and B together. The only thing we don't know is the initial velocity of object B, and that's what we worked out at the beginning we'd eventually need to solve for. Stating a particular direction convention, I'm taking east as positive. The first thing you need to state is something to do with momentum conservation, which are basically either of these first two lines. This first line here, I have the sigma sign, sigma pi, which means the sum of your momenta initially, and that equals the sum of your momenta finally, after the collision. So I here, the subscript I stands for initial, that's before the collision, and the subscript F stands for final, and that is for after the collision. Moving into the second line, the total momenta of your system initially, it is the momentum of object A, the momentum of object plus the momentum of object B, and that is equal to the momentum of your interlocked vehicle system, which is mass A plus mass B multiplied by the total speed V that they have together. Now, substituting in here, the only trick is to make sure that all your velocities, VAI, VBI, and V, are in line with a particular direction convention, which is why I was quite careful to state it first. East is positive in my particular case, which means because vehicle A was traveling east, this is a positive 12.5. The initial velocity of object B, well, that's what we're looking for, so we can't substitute anything in here. But when we eventually get to it, we'll need to read it in light of this direction convention. And then in question 4.3, we came up with an answer of 4.58 meters per second. Yet we need to take the direction into account. So you can't just take the 4.58 meters per second, the speed that you were asked for in 4.3. You do actually need to put in this negative sign here because the vehicles are moving west after the collision, which is in the negative direction. Performing that calculation eventually yields the initial velocity of B as negative 15.97 meters per second. You can't just stop there. We need to interpret what this negative sign means. Negative with our particular direction convention means to the west. The biggest misconception in question 4.5 was somehow many of you seemed to think that the forces were different in size because the masses of the various vehicles were different in size. Newton's third law. Newton's third law says that the forces must be equal in magnitude. If body A exerts a force on body B, if car A exerts a force on car B, then car B must exert a force on car A. This force must be equal in magnitude, but opposite in direction. So the first thing you needed to conclude, or as part of your conclusion, is that the forces are equal in magnitude. Okay. Now, if the forces are equal in magnitude, but vehicle A is lighter, it will experience a greater acceleration. And that comes from acceleration is equal to F over M. If M is smaller for A, and if M is smaller for A, and if F is the same, well then the acceleration of car A will be bigger. So vehicle A has the greater acceleration. So if it has a greater acceleration, it has a greater change in velocity, and thus the driver of vehicle A is more likely to be injured. Question 4.6. 4.6, you're showing by calculation whether the collision was elastic or inelastic. We basically already said that this collision must be inelastic, and that's because these vehicles lock together. There is no way that if they lock together you can have an elastic collision, and you can keep that in mind for future questions of this particular type. The biggest thing that you need to remember is that we are working with the kinetic energy of the system, not the kinetic energy of individual objects. And that's the significance of the sigma sign over here. We're calculating the sum of the kinetic energies initially, so that's the total kinetic energy of the system. That's kinetic energy of object A initially, plus the kinetic energy of object B initially. Performing that calculation, we end up with this number here, 646,000 roughly joules. Performing the calculation for the final kinetic energy of the object, well, we've actually just worked that out already. That must be the 63,000 joules that we calculated earlier, because when your object came to rest, it obviously had no more kinetic energy, and just after the collision, it must have had 63,000 joules worth of energy in order for friction to have done work of negative 63,000 joules. So here we can clearly see that the initial kinetic energy of your system is greater than your final kinetic energy of the system. Therefore, kinetic energy is not conserved, and your collision must be inelastic.